Hello, Science 10, and welcome to our lesson on acids and bases. Today, we are going to learn the difference between acids and bases based on properties such as pH, taste, touch, and litmus. We're going to define the word aqueous as well as learn the rules on how to name acids. So let's start talking about the basics. This should be a little bit of a review from last year. And although some of you were online last year, this is something we did talk in extent about because it is important for Science 10. So acids and bases. In real life, you can go to your kitchen and grab a couple different things. Maybe you grab some orange juice to drink for breakfast, you make yourself an egg, and then, you feel like, oh, I'm going to go and clean my house. Okay, yes, maybe those are not things you do, but essentially what you used are a bunch of acids and bases. At home and in real life, there's a lot of things that we can touch and taste that are acidic or basic, and they're not harmful to us. So we have the properties of sour tasting acids and bitter tasting bases based on the fact that there are common household items that can be eaten or touched and felt and tasted that won't harm us. However, in a chemistry laboratory or in the lab, we never touch or taste any chemicals. So although we talk about the properties of acids and bases based on bases are slippery to touch and bitter tasting and acids are sour, we would never do that in a lab. So in the lab, we have to turn to something else, and those are called indicators. They help us determine if something is an acid or base because we will never touch, drink, or hold an acid or base. We don't know how dangerous they are. So in the lab, we have a thing called litmus paper, and litmus paper can be both red or blue. And blue litmus paper in the presence of an acid will turn red, and red litmus paper in the presence of a base will turn blue. So essentially, we have two different types that tell us if something is an acid or a base. And the way we like to remember is red is acid, blue base. So if you have blue litmus paper and it stays blue, it's a base. If you have blue litmus paper and it turns red, it's an acid. So acids and bases have very distinct properties that make it very useful for us to use. These are them. Now, again, as a reminder, we will never taste anything in the lab, but we do know that acids as a property have a sour taste and bases have more of a bitter. The thing about acids is we don't touch them because they burn, usually. Think about a little bit of vinegar on your hand. If you have a cut, it burns. But the thing about acids we know is that they readily react with metals. They cause bubbling on the surface of metals. So they're reacting and causing a chemical reaction. Bases are more slippery and don't react as much. The one that I need you guys to remember, this one is really key, is pH. Acids have a pH of less than 7. So the pH scale is 0 to 14. Acids take up 0 to 7. Bases take up 7 to 14. So it's split into two. You need to know where they fall on the pH scale. If I said a pH of 3, you should say acid. If I say pH of 10, you should say base. Both of them conduct electricity and both of them are corrosive. Last year, some people did an activity where we saw how strong acids and weak acids versus strong bases and weak bases conduct electricity. The stronger the acid or stronger the base, the brighter the light bulb goes. And that's just because they dissociate or become ions. There's more ions in the liquid to cause the conductivity to occur. So what we have in the lab, like I said, is something that we use that is called an indicator. And why we use them is because we need to know how strong an acid or a base is. Litmus paper is a great indicator to say it's an acid or it's a base. But what it's not good at is it's not good at measuring the strength of the acid or the bases. So if you went into the lab and sat down at a table and there was 3 clear liquids in front of you and you dumped your papers into all 3 and all 3 came up red, you'd be like, oh, they're acids. Great. But you don't know if one of them is vinegar, 7-Up, or hydrochloric acid. You don't know the difference between the 3. All you know is that they're acids. But with pH scales and pH paper or what we call universal paper, you can actually find out the pH of what you are looking at, which is really important because hydrochloric acid would burn you. Sprite you can drink. So what happens is if you start off at the pH scale of 14 and work your way backwards this way, you actually become 10 times more acidic with each step down that you take. Now, like I said, most of the indicators we use are going to be pretty simple. There's universal indicator paper. Litmus paper is really common because it's easy to make. It's made from lichen. It's super inexpensive. But we also have other things like bromothymol blue, phenolphthalein, methyl orange, methyl red, lime water. All of these are indicators that tell us if something is an acid or a base. So here is just an example of the pH scale starting from 0 to 14. And you can see along the side the hydrogen ion concentration. You can see that the stronger it is as an acid, the more hydrogen ions it has. Now, something you may hear later this year, and as you move into chemistry, is that acids are made out of something called the hydronium ion, meaning they have hydrogen, where bases are made out of something called hydroxides, which are OHs. But for us right now, it's fine. We're just going to refer to it as the stronger the acid, the more hydrogen ions it has. So now we're going to move into talking about how to define an acid and how to name them. So there's lots of different types. There's carbonic acids and citric acids and phosphoric acids. And you can find all of these in Coke or in your lemon juice. So we have acids in a lot of things. Acids wear away at the enamel of your teeth. That's why using these kinds of things over a long period of time can actually harm your teeth. Things like that. So what makes a substance an acid? Arrhenius, who is that lovely guy you see there, proposed a theory that an acid is a substance that reacts and releases hydrogen ions in water. So for example, when we take hydrogen chloride, there we go. Sorry guys. When we take hydrogen chloride gas and we put it in water, our hydrogen ion dissociates, and so does our chloride ion. So what we use is this new type of state called AQ, or aqueous. It essentially means that a substance is in a solution with water. That's all it means. Aqueous is in water. All acids, when we learn to name acids, all acids have an aqueous state. And that is because all acids that we are going to name come from ionic compounds, which start as solids and then become aqueous when we put them in water. Okay. Now, that being said, if something is aqueous, okay, you see the AQ beside it, it does not mean that it is always going to be an acid. So a base will release an OH or a hydroxide ion when in solution. So acids are hydrogens, bases are hydroxides, so the OH. So for example, when we add sodium hydroxide to water, okay, it becomes the sodium ion in aqueous state and the hydroxide ion in aqueous state. All right. Now, if we were to look at acids and bases and want to deal with them and neutralize them, neutralization essentially means we're going to put an acid and a base together, and they end up producing salt, water and salt within that compound. Okay. So if we were to take our last two examples, sodium hydroxide and hydrogen chloride, okay, and they're both in liquid, hence why they show the aqueous state, they would end up causing a reaction that gives us water and salt, right? And that's how neutralization occurs. So let's get started off by talking about how to name acids. So your examples as we name are a little bit different than mine, but essentially it's pretty much the same. If you see a chemical formula with hydrogen bonded to a bunch of other nonmetals in solution, this compound will have special naming rules, okay? So acids will always have hydrogens first, except for that one right there, which I cannot remember its name. Oh my goodness, you guys, I'm blanking. It's fine, it's on polyatomic. So to name acids, you first have to name them using the rules for ionic compounds you've already learned, okay? So for example, if an ionic compound is named and it ends in IDE, okay, we're going to change its name to hydro something ic acid. So hydrogen chloride. we've already seen this one. Your example is hydrogen iodide, okay? So HI. Essentially, it works in the same way. You go from hydrogen chloride to taking it and combining it as one word, and instead of writing hydrogen chloride as two words or hydrogen iodide as two words, you're going to combine it, you're going to combine it into this, hydrochloric acid. So you take the IDE ending away, take hydro from hydrogen, and rename your chloride into chloric acid, and then you add acid at the end. So this one would be hydrosulfuric or hydrosulfic acid, the second example, okay? In your notes, you would go from hydrogen iodide to hydrogen hydroiodic acid, all right? So that's the first naming rule. There's lots. They're in your book, your your formula chart, so don't worry, but we do need to talk about it. So here, I gotta do this again, guys, sorry. Here we have the ionic name ending with ATE. So ATE happens when we are talking about polyatomics, phosphate, sulfate, nitrate, chlorate, those kinds of things. So if a name ends with ATE, we're going to not put the hydro this time. We're just going to have the ic acid. So in your notes, you're doing hydrogen sulfate. So it's hydrogen sulfate, HSO4, and it becomes it becomes sulfuric acid. My examples are shown here. Now, same idea. I have the first one spelled different. You can spell it either way, sulfuric acid. But another example would be hydrogen chlorate, which is HClO3 aqueous. This becomes chloric acid. We drop the hydro this time, and we just call it chloric acid or sulfuric acid. Now, let's just do that. Sorry, guys. Now the next naming rule is ITE, nitrite, phosphite, sulfite, those kinds of things, okay? So this time we're talking about hydrogen chlorite and hydrogen nitrite. So the first example I have is hydrogen chlorite would become chlorous acid. So ITE just becomes OUS. Your example, hydrogen nitrite, just becomes nitrous acid. So there's, like I said, a lot to remember here, but let's just put them in our notes. Okay, nope, right. Now, there's a couple more here that we just need to run through. If the name ends in per-ate, we're going to change it to per-ic. Now, again, this is a very, this one you don't have in your notes, and that's okay. We don't work a lot with hydrogen per-ates and to turn them to per-ics, so don't worry about this one. I just want to show you it. Okay, so it seems like I have these things everywhere. All right, so the last rule we have is if the ionic name ends in hypoite, we're going to change it to hypous. So the one you have is hydrogen hypochlorite. This one here, HClO. Hydrogen hypochlorite becomes hypochlorous acid, right? So thank you for following along. Today's goals was, like I said, to learn the naming, to talk about acids and bases, which we did. Now, you don't have to have that naming part memorized. We're going to do lots of practice, and it is on your formula sheet. Have a good night, and I'll talk to you soon.